Hey everyone, welcome back to Chem Story. Alright, today we're going to talk about bond length and how it's related to bond strength. Now, you might be wondering, why do we even need to care about this? Well, it turns out that understanding bond length and strength gives us a lot of insight into how molecules behave. It helps us predict reactivity, stability, and even which bonds are easier to break in a chemical reaction. So this isn't just some theoretical concept. It's actually a powerful tool for understanding real chemistry. Let's break it down step by step and see how these two ideas are connected. So, what is bond length? It's simply the distance between the nuclei of two atoms when they form a stable molecule through covalent bonding. We usually measure it in picometers or angstroms. 1 picometer is 10 to the negative 12 meters, and 1 angstrom is 10 to the negative 10. So basically, 1 angstrom is the same as 100 picometers. Now, you might be wondering, why do different bonds have different lengths? Well, it mainly comes down to 3 things: atomic size, hybridization, and bond order. These factors work together to determine how bond length changes depending on the molecule. First, atomic size plays a big role. If we compare atoms across the same period, they actually get smaller as we move to the right on the periodic table. And because smaller atoms can get closer to each other, this usually results in shorter bond lengths. On the other hand, if we look at atoms within the same group, they get larger as we move down the periodic table. And because larger atoms have electron clouds that spread out more, the distance between their nuclei increases, which leads to longer bond lengths. Now, let's talk about 2 major factors that affect bond length: hybridization and bond order. To keep things simple, we'll use carbon-carbon bonds as our main example. From a hybridization perspective, bond length is influenced by the type of hybrid orbitals involved in bonding. The key idea here is S character. Orbitals with more S character pull the bonding electrons closer to the nucleus, which makes the bond shorter and stronger. That's why a bond between 2 sp hybridized carbons is the shortest, while a bond between 2 sp3 hybridized carbons is the longest. Now, looking at it from the bond order perspective, bond length depends on how many electron pairs are shared between the atoms. A single bond involves just 1 sigma bond. A double bond has 1 sigma and 1 pi bond, and a triple bond has 1 sigma plus 2 pi bonds. The more bonding interactions there are, the more tightly the atoms are pulled together. So the trend in bond length is pretty straightforward. If we look at the actual bond lengths, we can clearly see this trend. A carbon-carbon single bond is about 154 picometers. A double bond is around 133 picometers, and a triple bond is the shortest, at about 120 picometers. The same idea applies to CH bonds too. Here, the bond length changes depending on the hybridization of the carbon atom. Since hydrogen only has a 1s orbital, the bond length is completely controlled by the carbon it's attached to. As the S character increases, the bonding electrons are pulled closer to the nucleus, which makes the bond shorter. So CH bonds with sp3 hybridization are the longest. sp2 hybridized ones are a bit shorter, and sp hybridized ones are the shortest. A CH bond with sp3 hybridization is about 109 picometers. With sp2, it's slightly shorter, around 108 picometers. And with sp, it's the shortest, about 106 picometers. The differences might seem small, but the trend is clear. As S character increases, bond length decreases. This same trend isn't just limited to carbon-carbon or carbon-hydrogen bonds. You can also see it in carbon-nitrogen bonds, especially when you compare different types of amines and amides. Take a look at aniline on the left and isopropylamine on the right. We can compare their CN bond lengths by looking at the hybridization of the carbon attached to the nitrogen. In aniline, that carbon is sp2 hybridized. In isopropylamine, it's sp3 hybridized. Because of that, the CN bond in aniline is shorter than the one in isopropylamine. And again, this follows the same trend we've been talking about. CN bonds involving sp2 hybridized carbons are shorter than those involving sp3 hybridized ones. We see a similar trend when we compare acetamide left and ethylamine right. and that's mostly due to differences in the hybridization of the carbon bonded to nitrogen. In acetamide, that carbon is sp2 hybridized, while in ethylamine, it's sp3 hybridized. And since sp2 hybridized carbons have more S character, they pull bonding electrons closer to the nucleus. That's why the CN bond in acetamide is shorter than the one in ethylamine. There's another factor at play too: resonance. In acetamide, the lone pair on nitrogen can delocalize into the carbonyl group, creating resonance. This increases the bond order, giving the CN bond partial double bond character, which makes it even shorter. On the other hand, ethylamine doesn't have that resonance, so its CN bond stays a typical single bond and ends up being longer. So in this case, both hybridization and resonance work together to make the CN bond in acetamide shorter than in ethylamine. And again, the same basic principles apply. More S character means a shorter bond, and a higher bond order leads to a shorter bond as well. Now that we've looked at how bond length varies, let's talk about how it connects to bond strength. Here's the key rule to remember: bond length and bond strength are inversely related. In other words, the shorter the bond, the stronger it is. That's why triple bonds are the strongest. They're also the shortest. Double bonds come next, and single bonds are the longest and the weakest. This happens because more overlapping orbitals create greater electron density between the atoms, which makes the bond stronger and harder to break. And this isn't just a general trend. We can actually see it in the numbers. It's supported by bond dissociation energy, or BDE, which tells us how much energy is needed to break a bond. For carbon-carbon bonds, a single bond between two sp3 hybridized carbons has a bond dissociation energy of about 348 kilojoules per mole. A double bond between two sp2 hybridized carbons is stronger, with a bond dissociation energy of around 612. And a triple bond between two sp hybridized carbons is the strongest, with a bond dissociation energy of about 839 kilojoules per mole. To wrap things up, bond length follows a pretty clear trend. It gets shorter as we move from a single bond to a double bond, and even shorter when we go from a double bond to a triple bond. We see a similar pattern with hybridization too. A bond between two sp3 hybridized carbons is usually the longest. Next comes the bond between an sp3 and an sp2 hybridized carbon. And the shortest bond is between an sp3 and an sp hybridized carbon. So in both cases, whether bond order increases or the S character increases, the bond gets shorter. That's all for today. If you have any questions, feel free to ask, and thanks for watching.